Hello everyone. Welcome to the classroom of Advanced Manufacturing Technologies for Welded Structures. Today, we will delve into the fundamental knowledge of waterjet cutting together. I am your lecturer, Zhong Xinghe. As an advanced processing technology, waterjet cutting is widely applied across various industries, including industrial manufacturing, architectural decoration, and the medical field. Through this lesson, we will explore the principles, characteristics, and applications of waterjet cutting and comparisons with other cutting technologies. I hope everyone will listen attentively and engage actively. Let's begin with the basic principle of waterjet cutting. The core of waterjet cutting lies in the formation of high-pressure water jets. The high-pressure pump pressurizes water to an ultra-high pressure state, up to 4,000 megapascal, through an extremely small nozzle with an aperture of 0.1 to 0.4 millimeters. It generates a high-speed jet with a velocity of approximately 1,000 meters per second. In abrasive cutting, abrasives are mixed with the water jet to cut hard materials through kinetic energy impact and grinding, achieving higher cutting efficiency. The water jet cutting system comprises several key components. 1. High-pressure pump and CNC platform. The high-pressure pump supplies ultra-high-pressure water above 600 megapascal, serving as the core power source for water jet cutting. The CNC machining platform enables precise X/Y-axis movement, capable of cutting complex curves with an accuracy of up to 0.01 millimeters. 2. Jet cutting head and abrasive supply system. The jet cutting head features gemstone nozzles, such as sapphire or diamond, that are resistant to high pressure and have strong focusing ability, ensuring a stable jet flow. The abrasive supply system is responsible for storing and metering abrasives, ensuring uniform mixing and enhancing cutting performance. 3. Cooling system. The cooling system maintains stable equipment operation, prevents overheating and damage to key components, such as the high-pressure pump, and extends the service life of the equipment. As shown in the figure, waterjet cutting can be classified according to shape, pressure, and working principles. For example, 1. Classification by shape and size. Small waterjet cutters, for laboratories and small-scale processing. Medium waterjet cutters, for general industrial production. Large waterjet cutters, for processing large workpieces. 2. Classification by pressure level. Low pressure, below 100 megapascal. Limited cutting capability, mainly for soft material processing. High pressure, above 100 megapascal. Good cutting performance, widely applied. Ultra high pressure, above 200 megapascal. Strong cutting capability, capable of processing ultra hard materials. 3. Classification by working principle. Pre-mixed waterjet cutters. Abrasives are mixed in advance. Different types of waterjet cutters are suitable for different processing needs. A notable feature of waterjet cutting is its strong versatility. It can cut almost all materials, whether soft materials such as foam, rubber, or hard materials such as metal, stone, ceramics. Waterjet cutting is capable of metal plate blanking or composite material processing with extremely strong versatility. It is widely used in industries such as automotive, aerospace, construction, and medical, satisfying the material processing demands of different sectors. Another feature of waterjet cutting is its cold cutting property. Waterjet cutting produces no heat-affected zone, preventing material deformation or ablation, making it particularly suitable for heat-sensitive materials, such as titanium alloys, composite materials. For example, in the medical field, Waterjet cutting can be used for manufacturing orthopedic implants. The cold cutting property protects the original properties of the material without compromising its mechanical or chemical properties. For example, waterjet cutting of titanium alloy parts ensures the material's high strength and corrosion resistance in the aerospace industry. Waterjet cutting is characterized by high precision and high material utilization rate. The kerf width of waterjet cutting is small, 0.8 to 1.8 millimeters, and the cut is smooth, below our A 3.2 micrometers. The surface is neat and smooth, requiring no secondary processing. For example, waterjet cutting can achieve fine pattern engraving with smooth, burr-free cuts in glass art carving. In addition, it can cut the complex shapes and improve material utilization. For example, for the metal plate blanking, waterjet cutting can optimize nesting according to part shapes to improve material utilization. Waterjet cutting features environmental friendliness and high efficiency. The medium for waterjet cutting is only water and natural abrasives, with no dust or chemical pollution, has pretty environmental protection requirements. For example, waterjet cutting can significantly reduce dust pollution and improve the working environment in stone processing. Additionally, the equipment features low energy consumption, low operating costs, and high cutting efficiency. In composite material processing, waterjet cutting can swiftly complete cutting tasks, thereby improving production efficiency. Waterjet cutting is characterized by high cutting surface quality. The surface remains neat and smooth after cutting, free from damage, and requires no secondary processing, making it ideal for high-precision processing. Waterjet cutting achieves high-precision machining to meet the requirements of high-precision parts. Next, let's explore the typical applications of waterjet cutting. Waterjet cutting is extensively used in industrial manufacturing. 1. Waterjet cutting of metal plates is highly efficient, delivers excellent cut quality, and can cut the complex shapes. For example, waterjet cutting is employed for blanking body parts in the automotive manufacturing industry. 2. Waterjet cutting of composite materials causes no thermal damage, preserves material properties, and offers high processing precision. In the aerospace field, it is utilized for cutting carbon fiber composite materials. 3. Waterjet cutting is well suited for processing special materials with no heat-affected zone, ensuring the high cutting quality. It is used for cutting titanium alloy implants in the medical device manufacturing. In the architectural decoration field, waterjet cutting can be applied to stone mosaic patterns, glass heart carving, and ceramic profile cutting. For example, with the waterjet cutting technology, stones can be cut into complex pattern mosaics with high cutting precision, smooth surfaces, and excellent decorative effects. Fine art carving can be performed on glass with smooth, burr-free cuts, suitable for high-precision processing. Ceramics can be cut into special shapes with high cutting quality, suitable for processing complex shaped ceramic products. Waterjet cutting is also widely used in the medical field. For example, it can be used for manufacturing surgical instruments, tissue debridement, and processing medical devices. Additionally, waterjet cutting is suitable for special scenarios such as oil pipeline cleaning, nuclear facility decommissioning, and ultra-hard material processing. Optimizing waterjet cutting process parameters is crucial for enhancing cutting efficiency and quality. For instance, the water pressure range is 200 to 620 megapascal, which can be adjusted based on material hardness and thickness. The flow rate range is 3 to 10 liters per minute. Jet concentration and cutting depth shall be balanced. Cutting speed is tailored to material thickness and type. For example, Speeds can reach 2,000 to 5,000 millimeters per minute for cutting rubber, while for thick metals, speeds are typically 50 to 200 millimeters per minute. In the case of rubber cutting, speeds are up to 3,000 millimeters per minute, showcasing high cutting efficiency. Path optimization can be achieved through CNC multi-axis linkage and AI algorithms. For example, a 5-axis linkage CNC system can deliver high-precision cutting for complex shapes, thereby boosting production efficiency. The selection of abrasive type depends on material hardness. For instance, emery is required for cutting ceramics, with an abrasive flow rate generally set at 200 to 500 grams per minute, or higher flow rates for harder materials. Nozzles shall be selected according to service life and precision. For example, diamond nozzles can ensure cutting quality and extend service life in high-precision applications. The standoff distance is typically 1 to 5 millimeters, but can be adjusted to 3 to 8 millimeters for thick materials. Excessive standoff distance may compromise cutting precision. For example, when cutting thick metal, the standoff distance can be appropriately increased to ensure effective cutting. Compared to technologies such as laser, plasma, and wire cutting, waterjet cutting offers advantages such as cold cutting, compatibility with multiple materials, and environmentally friendly operation. However, it does have a slower cutting speed for thick metals, which is an area that requires further improvement. Today's lesson ends here. I hope you've gained something useful. If you still have questions, feel free to communicate after class. Thank you.